All right, good morning, everybody. Unfortunately, I'm not with you today. I'm working on a bit of a sore throat, but I'm hoping that I'll be better by Monday. So we're going to start with this warm-up. How many protons, neutrons, and electrons would you expect to find in this particular ion? All right, well, let's look at it. If we have uranium, we know that it has a atomic number of 92 on the periodic table. So that already tells us that there are going to be 92 protons. And I'm going to pause here for a minute because I want to help you remember what charge things have and where they are. So protons, you notice it starts with the pro. Well, pro means positive, so that tells you that protons are positively charged. Here's what that atomic symbol would look like. So it has a mass of 1, a charge of 1. And that's going to be in our nucleus. Then we can calculate our neutrons. We've got that mass number of 238. We know that the mass is a combination of our protons and our neutrons. So we can say, all right, well, we know we've got 92 protons. Adds up to 238, so there must be 146 neutrons. And again, if we look at the word, we can figure out that neutrons must be neutral. That means they have no charge. So here's what that's going to look like. So they have a mass of 1, so they're just as big as protons, but they have no charge. And then finally, we've got our electrons. Now, unlike what I had you do last time, this one is not actually a neutrally charged atom. It's got a charge. Now, it's a 2+. Now, if you look back at your packets, you'll see on number 16 that we calculate our charge with our protons minus our electrons. And apologies if your packets aren't back yet. So we know we must have 2 more protons than we do electrons, which means we have 90 electrons. Unfortunately, I don't have a really good mnemonic for you here. We need to remember that electrons are negatively charged. They help balance out the positive charge of the protons, and their mass is so small compared to protons and neutrons that it's rounded to 0 in that nuclear symbol. They do have charge, but if you remember the size of those beads, those silver beads, it's actually even smaller than that. That's just as large as I needed them to be for you to be able to count. So we have a 0 here. It is rounded to 0. It's not actually 0, though. So what I would like you to do now is in your notebook, you're going to draw this circle, and I want you to write what each of these things tells you. Make sure you include how you would calculate it or what's in it. The idea is this is your guide to how you're going to solve problems later. So for example, don't just say that this is the mass number. Okay, well, how do you calculate the mass number? What's in it? All right, I'm going to give you a couple other vocab words that you guys saw last time in the pivot, but I'm going to help you with some mnemonics here. So the first one is cation. I want to point out it's not cation. I know it looks like it, but it's cation. And the way you're going to remember is that it is positively charged. So that is an ion that is positively charged. An anion is negatively charged. So let's take a look at some examples. So here, this is our neutral potassium. The next one down is a cation because it's positively charged. And the next two are anions. All right, I'm going to have you take a minute and fill in the blanks in this table. It is in OneNote, so if you would rather do it there, you can. You can do it in your notebook, or you can just write it down on a scratch piece of paper. All right, now I'm going to have you go ahead and check. How did you do? Now, side note, what's really interesting, I want to point out we've got potassium 39 and potassium 40. What do we call those? All right, now, are these two isotopes? All right, so if we think about a food that has a lot of potassium we find in bananas, and potassium is distributed, different isotopes, throughout anything that contains potassium. So that means that bananas contain radioactive potassium. We're going to talk more about why I'm not super worried about it next time. All right, I want to talk to you about a real world use of radiation though. So when we're treating thyroid cancer, we treat it with iodine 131. So I'm going to have you chew on this for a minute. How many protons, electrons, and neutrons are in iodine 131? You're going to enter that on the side. And then I want you to figure out, how do the numbers of those 3 subatomic particles change when it breaks down to the non-radioactive xenon 131? All right, so just like before, we look at iodine is 53, so we know it's got 53 protons. That must mean that we have 78 neutrons, and it's neutral since I haven't told you otherwise. So 53 electrons. So if we look at xenon 131, we've got, wait a minute, now it's 54 protons and 77 neutrons and 54 electrons. So that means that it had to have lost a neutron and gained a proton and an electron, which is fascinating. We're going to talk more about that next week. But the reason that it does it is to change stability in the atom. So I want to remind you guys, we said protons have positive charge, neutrons have no charge. Those are all in the middle in that nucleus, so they're all smushed together. Well, here's the thing. If we have too many protons, those are all positive charges. If you remember from physics, if you tried to push the positive sides of magnets together, they pushed each other apart. And the same thing happens if we have two positive charges. Now, if there's enough neutrons in between those protons, they can help balance that out. But if you have too many protons and not enough neutrons, they're going to push each other away. Now, if you have too many neutrons, that's not as big a problem. It can accommodate it, but at a certain point, it just gets too big and bulky and it ends up breaking apart. Now, the way that we talk about whether or not something wants to stay together, an atom, or specifically a nucleus, wants to stay together versus how likely it is to fall apart and produce new atoms is called its stability. And we talk about it in terms of a half-life. So the half-life we represent by T half, and that's the time for half of the nuclei in a sample to decay to products. So we're going to do the Skillium lab in Pivot. Essentially, what you're going to have is you are going to have this radioactive form. This is our scary radioactive isotope, which I'm going to mark as S with a star. So remember, it's scary and should not be eaten. Now, you're going to take all of your Skittles, put them into a cup, and roll them onto the paper towel, assuming you want to be able to eat them later. Some of them are going to decay into the not scary and totally safe to eat blankium. And all this is in your Pivot lab, by the way. So you're going to record how many decay each time you roll. So let's say, for example, the first time you put all 40 in, and you have, after you roll, we're going to say you have 30 that are still an S, and then you have 10 that are a blankium. You're going to take these 30, put them back in the cup, and re-roll and see what you get. You're going to record that in your table. So here's that table. So let's say we're going to use our example that you had 30 S's remaining. You rolled, and when you rolled, you got 10 blankiums. That means in total, if you moved all those blanks that you got to a paper towel, you would have 10 total. So now you take those 30 and you re-roll those. Okay, well, let's say that, I don't know, half of them flip over. You have 15 that stayed an S, 15 that became blankium. So if you move those to your blankium paper towel, now you have 10 plus 15, which is 25. And you're going to go on and so forth until all of them are blanks. Then from there, you're going to look at your graph and you're going to figure out how long it takes for them to drop from 40 to 20. And if you notice, there's not a really even space here. So what you can do is do a line graph and you're going to estimate. Well, 20 right here is about 1.6. So that's going to be the half-life here for half of it to decay. Then you're going to see, okay, how long did it take to go from 20 to 10? Same estimation. Then you're going to take the average of 6 and 7 for number 8. So you need to finish that pivot lab by the end of class. Then you are going to go ahead and come back over here. You're going to make sure that you have the T-half for your Skidlium. And then you're going to start the LT 3.3a practice. Now, this is not going to deal a ton with half-life. It's actually going to be focusing more on those nuclear symbols again, but we're going to start talking about radiation, radioactivity, using those different nuclear symbols. We'll get to half-life more next time. All right, go ahead, go and do. If you are planning on eating the Skittles, make sure that whoever is actually doing the rolling washes their hands really well and that you roll onto those paper towels. Have fun, and I'm hoping to see you Monday.